In 1825, ships crowded the Thames, while work began on something that could not be seen from the river. At Rotherhithe, on the south bank of London, a circular brick shaft was sinking into the ground. The plan was simple to describe and difficult to believe. Build a road beneath one of the busiest navigable rivers in the world without stopping the traffic above. London needed another crossing. Docks and warehouses pressed against both banks, while goods, carts, workers, and boats moved through a port of enormous scale. Bridges were far away from this stretch of river, and ferries had limits. Marc Brunel proposed a different route. Instead of going over the Thames, traffic would pass underneath it. Brunel's answer was a moving iron shield, patented years before the work began. He later described finding inspiration in the shipworm, a small creature that bores through timber while protecting the opening around its body. His machine would try to do something similar in wet London ground. Before the shield could move, workers needed a way down. They built a huge iron ring at Rotherhithe, laid brickwork on top of it, and removed soil from inside. As the ground disappeared, the heavy circular wall settled downward under its own weight. The shaft eventually became the entrance to the underground works. The tunneling shield waited at the bottom. It was not a round cutting wheel like a modern tunnel boring machine. It was a broad rectangular structure made from 12 iron frames arranged across 3 levels. Together, they formed 36 separate working cells. One miner could stand in each cell, facing the earth directly ahead. The face of the tunnel was covered with wooden boards held tightly against the soil. A miner removed one board, scraped away only about 4 inches of ground, and replaced the board before moving to the next. The action was small by design. The riverbed had to remain supported while the opening advanced almost invisibly beneath it. When every miner had completed the same narrow cut, screw jacks pushed part of the shield forward. Bricklayers followed immediately behind, adding another course to the permanent tunnel. Excavated clay traveled backward in barrels and wheelbarrows, then rose up the shaft to the surface. Progress came from hundreds of careful repetitions rather than one dramatic machine. Above them, ordinary river traffic continued. Barges, sailing vessels, and steam craft crossed the line of the tunnel while 36 men worked behind timber boards below. The contrast was the point of Brunel's method. The shield supported the unstable face long enough for the masonry behind it to become the new structure. The working environment was harsh. Air moved poorly through the excavation, lamps burned in enclosed spaces, and polluted river water found its way into the ground around the shield. The men were not simply digging clay. They were working beneath a tidal river, whose bed had been disturbed by anchors, dredging, and years of heavy shipping. The shield reduced the chance of a sudden collapse at the face, but it could not remove the pressure of water or the uncertainty of the ground above. In May 1827, water broke through into the tunnel after the shield had advanced hundreds of feet. A diving bell was lowered over the site, and the damaged ground was packed so that the tunnel could be pumped out. The operation shows how unusual the project had become. Men were repairing an underground work from the river itself, while the shield and brickwork waited below. Work resumed, but the Thames remained physically close to every new course of masonry. A second major flood followed in January 1828. 6 workers lost their lives, and the younger engineer Marc Brunel was badly injured. The episode is part of the tunnel's history, but its longer consequence was quieter. Confidence and money drained away. The accident forced months of recovery and repair, and the company struggled to raise enough capital to continue. By August, the unfinished passage was closed off behind brickwork and construction stopped, leaving the shield beneath the river with much of the crossing still incomplete. For years, the tunnel ended behind brickwork. The shaft remained in Rotherhithe, the river continued above, and Brunel worked to secure the money needed to continue. The project had begun as a public marvel and now looked to many observers like an expensive experiment that might never reach the opposite bank. Drawings, models, guidebooks, and demonstrations helped keep the idea alive. Even while excavation was silent, the tunnel existed in public imagination as a promise of what engineering might eventually make routine. Government support eventually allowed work to restart. In 1835, the old shield was removed and an improved replacement was assembled in the tunnel. The method did not become faster in any magical sense. The same logic remained. Support the face, remove a few inches, push the frame forward, and close the new space with brick. The improved works depended on the same discipline that had defined the first phase, but now the company had better financial support, more experience with the ground, and a clearer understanding of the river above. The revived works again moved beneath the river by increments. Timber boards held the clay, iron screws carried force through the shield. Bricklayers built twin horseshoe-shaped vaults behind the miners. Cross arches connected the two passages at intervals. The finished structure would extend for about 1,200 feet between Rotherhithe and Wapping. Each vault was wide enough for traffic that was expected to include carts, and the two passages together formed a broad brick box beneath the riverbed. The engineering was repetitive, but repetition was exactly what made progress possible. The permanent lining used brick set in Roman cement, with the two vaults carried inside a larger rectangular mass of masonry. From the river above, none of this geometry was visible. Flooding did not disappear. Further inundations came during the later years of construction, and pumping remained part of the system. When water found a weak place, the response was practical rather than elegant. Identify the breach, reinforce the riverbed, drain the works, repair what had shifted, and begin again. Yet by then the project had acquired something it had lacked during the long pause, a route to completion. In 1841, the main tunneling work was finished. The shield had done its final work, and the long underground shell could be paved, finished, ventilated, and prepared for public use. The completed passage was then lined and finished for the public, turning a construction site of clay, timber, iron, and pumps into an architectural interior. The tunnel that emerged was not quite the one its promoters had promised. It had been conceived for horse-drawn carts and goods traffic, with broad approaches leading gently underground. Those expensive ramps were never built. Access depended on stairways in the end shafts, which meant the new crossing opened as a route for people on foot. This changed the economics of the project before the first ordinary visitor entered. The engineering beneath the Thames had succeeded, but the transport system around it was incomplete. A tunnel intended to move commercial traffic would begin life as something closer to a public passage and spectacle. The end shafts were large enough to suggest the intended scale of the road approaches, but the missing ramps permanently changed how the tunnel would be used during its first decades. In March 1843, Londoners were allowed to walk beneath the Thames through the completed tunnel. The experience was unlike an ordinary bridge or ferry. Two long brick vaults stretched under the river, linked by repeated arches. Lamps illuminated columns, masonry, and a perspective that seemed to continue far into the underground distance. The river itself was invisible. There was no view of water, only the knowledge that ships and tides were passing somewhere overhead. For many visitors, that hidden relationship between ordinary London and the engineered space below was the attraction. The route was roughly 1,200 feet long enough for the entrance behind a visitor to disappear into perspective before the opposite bank was reached. The response was immediate. About 50,000 people entered on the opening day, each paying a penny. Within the first few months, roughly 1 million visitors had passed through. Some were simply crossing the river. Many came because walking beneath the Thames was itself a new London attraction. The tunnel had turned a technical achievement into a mass public experience. Visitors descended the long stairways, and entered the twin passages. Only a short time before, miners, bricklayers, pumps, and iron frames had occupied the same underground route. The one-penny admission also turned foot traffic into a source of revenue, even though it could not replace the freight business that the missing road approaches had been expected to support. The cross arches soon became small commercial spaces. Vendors sold souvenirs, refreshments, printed views, models, and other inexpensive goods. A printing press produced commemorative material inside the tunnel. Contemporary accounts and surviving objects show how quickly engineering became merchandise. Plates, guidebooks, tokens, small models, and illustrated keepsakes allowed visitors to carry a piece of the experience back into the city. What had been designed as transport infrastructure began to behave like an underground bazaar, with lamps, stalls, and crowds arranged inside brickwork that had been built under a working river. The repeated cross arches made natural shop bays, so commerce settled into spaces that had originally been structural openings between the two parallel passages. This unexpected use changed the atmosphere but not the engineering beneath it. Behind the stalls and lamps remained the brickwork laid immediately after the shield moved forward. Decorative columns and repeated arches gave visitors a finished interior, but the structure itself still recorded the logic of construction. Every short length of tunnel had begun at the face with timber boards holding back the earth. A miner had removed one board, taken away a narrow slice of ground, and replaced the support. The iron frames then advanced as bricklayers closed the gap behind them. The spectacular interior was the accumulated result of very small, controlled movements. Even the finished decoration could not hide the unusual proportions. Twin horseshoe vaults, repeated cross openings, and deep shafts at each end belonged to a machine-made route rather than a conventional street. The pedestrian tunnel never fulfilled the original commercial plan for carts and freight. Over time, the attraction lost some of its novelty, and the stair access made it less useful than the broad roadway Brunel had imagined. Yet the structure itself had solved a problem that would become increasingly important as cities grew. The shield had demonstrated a practical way to support soft, unstable ground, while a large passage was created beneath water. Later, tunneling machines would become vastly more powerful, but they would keep the same essential principle: protect the face, excavate within protection, move the shield, and build the permanent lining behind it. The Thames Tunnel therefore mattered beyond London. It was not a template to copy without change, but a proof that shield-driven tunneling could make a large subaqueous crossing practical. In 1865, the Thames Tunnel was sold to a railway company. The pedestrian fittings gave way to a different kind of traffic, and in 1869, steam trains began running through the old brick passages. The conversion required new railway approaches and altered the shafts, but the crossing beneath the river remained the work completed a generation earlier. Smoke and steam replaced the earlier crowds of pedestrians and souvenir stalls. The tunnel had finally become part of a transport network, although not the horse-drawn road its first investors had expected. Its second life was closer to Brunel's original purpose, carrying regular traffic through the city rather than simply attracting visitors. The railway conversion also demonstrated how durable the original masonry had become. A passage excavated for carts could accept a new transport technology decades later, without being rebuilt from the river bedward. Rail use continued and later became electric. The same crossing eventually formed part of London's underground railway system, surviving changes in operators, rolling stock, signaling, and the city above. After modern refurbishment, it returned to service as part of the London Overground. Passengers now move between Rotherhithe and Wapping in a few moments. Most have no need to think about the shield, the timber boards, or the years when the tunnel ended behind brickwork. Yet the trains still pass through the same historic river crossing, inside masonry whose basic form belongs to the experiment begun in the 1820s. Electric traction removed the smoke that had made steam operation unpleasant underground, while the 19th-century brick shell continued to carry the line beneath the same stretch of water. The Thames never moved aside for the tunnel. Ships continued above while miners worked below, protected by timber boards, iron frames, screw jacks, pumps, and fresh brickwork. The project survived floods, a long pause, financial uncertainty, and a change in purpose after completion. What lasted was the method: hold unstable ground long enough to create a permanent space inside it. London did not pass beneath the river in one grand motion. The route advanced through repeated acts of caution, each one only a few inches deep. 4 inches became another 4, and another, until an impossible route became ordinary infrastructure. The river still rises and falls above the route, while the movement below has become routine enough to disappear into the background of London life. The river stayed where it was. London simply learned how to pass beneath it.